This is one of a series of short videos designed to support and enhance your understanding of some of the key concepts contained within A-Level Further Mathematics. If you've already mastered the basics of a topic, then the videos should stimulate your thinking and provide further insight. The focus is on looking in a bit more depth at examples that can be tackled using knowledge gained within the curriculum. These examples are not taken from any particular exam specification and as such may go beyond what you need to know for your examinations. However, they all illustrate key concepts that will help you by giving you a more thorough understanding. In this video, I am going to look at how complex number equations that describe loci in Argand diagrams can be converted into Cartesian form. Here are two examples of loci that you should already be familiar with. In the first, we know that the modulus of z minus a is equal to some constant k forms a circle in the Argand diagram. In my example, we should recall that the modulus of z minus 2 plus I simply means the distance of our point from 2 plus I. And since we want this to be equal to 3, there's 2 plus I in the Argand diagram, we want all points that are a distance 3 away from 2 plus I, and so we get a circle, centre 2 plus I, radius 3. In the second example, you should recognise that the modulus of z minus a is equal to the modulus of z minus b, where a and b are complex numbers, forms the perpendicular bisector of points representing a and b in the Argand diagram. In my example, if we write this, or rewrite this as the modulus of z minus 2 is equal to the modulus of z minus 4 plus 3i, then we end up with negative 2, 4 and 3i in the Argand diagram, and the locus of points is the perpendicular bisector. I am now going to look at these types of loci in more depth and see how the complex number equations can be expressed in a more familiar Cartesian form. We begin with the first example and start by making a substitution. If we split z into its real and imaginary parts, then we can write z is equal to x plus yi. Making this substitution and gathering together real and imaginary parts, we have the modulus of x minus 2 plus y minus 1 lots of I is equal to 4. But we know that to find the modulus of a complex number, we simply take the square root of the real part squared plus the imaginary part squared, and that's equal to 4. If we square both sides of the equation now, we end up with x minus 2 squared plus y minus 1 all squared is equal to 16. And we recognise this immediately from our coordinate geometry as a circle with centre at 2, 1 and radius equal to 4, just as we'd expected from this equation here. In the second example, we start with the same substitution, so we say let z equal x plus yi. If we replace z by x plus iy on both sides of the equation, again gathering real and imaginary parts together, on the left hand side we have the modulus of x plus 2 plus y lots of I is equal to the modulus of, this time we've got x plus 4 as the real component and simply yi as the imaginary component. Evaluating the modulus on both sides, in the normal way we take the square root of x squared plus 2 plus y squared, and on the other side the square root of the real part is x plus 4, which we must square like this, and y squared. Squaring both sides and expanding the brackets all in one go, we end up with x squared plus 4 plus 4y plus y squared is equal to x squared plus 8x plus 16 plus y squared on the right hand side. If we subtract x squared from both sides and subtract y squared from both sides and tidy up a bit, we end up with 4y is equal to 8x plus 16 minus 4 is 12. Divide through by 4 and we get y is equal to 2x plus 3. So we have the equation of a straight line with gradient plus 2 and y-intercept of 3. We were expecting a straight line, but it's worth going back to the original equation and making sure that it is indeed the correct perpendicular bisector. Rewriting the original equation as the modulus of z minus 2i equals the modulus of z minus 4. I've used graphing software to plot these 2 points. So I've got minus 2 on the y-axis and minus 4 on the x-axis. If I select both points, I can use the perpendicular bisector tool to verify that the equation of the line is y equals 2x plus 3, which we can see just at the bottom of the screen there. And this is exactly what we found out algebraically. I think it's great to see here that we can make a connection between geometric and algebraic forms to gain a greater understanding of complex number loci.